So in class we were able to write down and prove this result related to moment generating functions. And namely, the result says that if you have a random variable with a moment generating function mx of t, then if you take the nth derivative of the moment generating function and then evaluate that nth derivative at 0, you'll get the nth moment of the random variable. So in particular, if n is equal to 1, you can get the mean, or the first moment, just by taking the first derivative and setting t equal to 0. So we didn't get a chance to do this example, but that's what we'll do on the next slide. So here we're supposing we have x, which is binomial np, and we want to show that the expected value of x is equal to n times p, but using moment generating functions. So we know how to do that from the definition of expectation, but here the goal is to use moment generating functions. So we'll start by taking the derivative of the moment generating function with respect to t, and then from there we'll set t equal to 0. So taking the derivative will involve a chain rule and a power rule, so we'll have n to the e raised to the t times p plus 1 minus p to the n minus 1, and then we need the derivative inside with respect to t. Well, only one term has a t, and that term will just be, so the derivative of this term here is just e to the t times p, and then the derivative of 1 with respect to t, 0, derivative of negative p with respect to t is also 0. Alright, so that looks like our derivative, and then the next step is to evaluate this at t equals 0. And that will give us an n times e to the 0 times p plus 1 minus p to the n minus 1 times e to the 0 times p. Well, this will simplify pretty nicely, right? This term here is just a p, e to the 0 is 1. Then we have a minus p, so we're just left with a 1 here. And then that's a 1 raised to some constant, so that will all be 1. This whole term here will be 1. And similarly, this e to the 0 is equal to 1, and we're just left with n times p. So we've shown just what we set out to show, that using the moment generating function and the theorem from the previous slide, that we get just what we should get, right? We get n times p as the mean of a binomial. Now maybe as an exercise for you, you can try to find the variance of a binomial, so the second centralized moment. Or if you're interested, you can find just the second moment, so the expected value of x squared, and see how that relates back to the variance. So there are lots of places that you could go from here using moment generating functions to find higher order moments or centralized moments.